and the student members, as well as other students who would like to participate in this webinar. So as you know, we have been conducting these for the past several months with the intention of educating our members on a variety of topics that they may not be knowing very well. Okay. So in that sense, these are all review talks to begin with, which can be followed by more technical talks. And we are very thankful to faculty members from colleges, universities, and research institutes who have kindly come here to deliver their talks on various topics. So these are talks which are meant to inform our members about developments in various fields, starting from the microscopic world to the macroscopic world of cosmology. And I must say, we have been quite successful in doing that. And in fact, we are doing the job of many universities. I feel universities and colleges should be arranging this kind of outreach activities, outreach programs for the benefit of students and the general public, which they are not doing, unfortunately. At least so far as physics is concerned, we are able to do these things for the benefit of teachers and the students all over Karnataka, and even from outside Karnataka, people have been joining, and we welcome them all to this program. And we've also conducted these talks in Kannada, also regional language, with the intention of encouraging higher education in the local language, that is Kannada, because it is our experience, and also, of course, your experience, or I think more or less, that most of the students and even unfortunately faculty members, including myself, we are not native English speakers. So we struggle. And that hampers the communication of knowledge, communication of information and exchange of ideas. So this should gradually go. And that would be the ultimate step of Atmanirbharta, not just the subject matter, but even the language. Because we should become self-reliant in not only the material, but also the delivery. So the students they speak confidently with the teachers and other faculty members. And I think, in my opinion, that is the ultimate step of Atmanirbharta. We are very far away from that particular, reaching that goal, unfortunately. Let's see what happens. And today would like to welcome today's speaker, Dr. Paniveni U.Shankar, for kindly agreeing to give a talk about the sun and super granulation. So before I request her,
Thank you, sir.
yeah, she may speak for about 15 minutes, followed by 10 minutes of question answer sessions. Before I request her to take over, I request Professor Rudraswamy, who is one of the joint secretaries of KPA and also a very good friend of Dr. Paniveni, to introduce the speaker. Over to Dr. Rudraswamy.
Thank you very much, sir, for this opportunity. So it is my great pleasure and privilege to introduce Professor Dr. Paniveni U.Shankar, presently serving as an honorary professor of physics at Poorna Pragna Institute of Scientific Research, Bengaluru, serving as a mentor at International Supernova Foundation to inspire young minds to pursue career in physics, serving as a volunteer for International Astronomical Union, obtained PhD in astrophysics from Mangalore University after carrying out collaborative research at Indian Institute of Astrophysics, Bengaluru, diploma in French language, Vidwat in Carnatic classical vocal music, having research experience of 20 years in the field of astrophysics, served in various academic institutions with the teaching experience of 34 years, superannuated as in-charge principal and professor from NIE Institute of Technology, Mysore, credited with many distinction and honors in academic field, recipient of National Merit Scholarship throughout academic career, secured 50th rank in SSLC, 4th rank in BSc, 1st rank in MSc Physics Solid State section from Mysore University, served as Research Associate of Inter-University for Astronomy and Astrophysics, Pune for many years, recipient of Indira Gandhi Sadbhavana, Rajiv Gandhi Excellence, Lifetime Achievement, and Leading Educationist of India Gold Medals. Delivered invited talks in international conferences held in countries like Italy, Australia, France, Belgium, London, Jerusalem, Istanbul. Served as a visiting faculty in Ethiopia and Middle East. Life member of many physics and astronomical society. Book with a chapter depicting her contribution to science has been released by INSA, New Delhi. Credited with many honors, distinction in the field of music. Regular artist of classical music for All India Radio and TV. Rendered a record of 55 concerts all over India. Invited as a judge to Yede Tumbi Haduvenu TV program coordinated by the legendary singer Dr. S.P. Balasubramaniam. Recipient of many prizes in All India music competition. Credited with the release of classical light music CD by Lahari Company. Credited to guide many disciples to get Vidvat in Carnatic classical vocal music. With this brief introduction, now I request Professor Paniveni U.Shankar, Madam, to deliver a talk on Sun and Super Granulation. My special request to Madam is that please devote a time to render a devotional classical song at the end of the talk. Over to you, Madam. Thank you very
Okay,
much.
sir. Yeah.
Thank you very much.
Thank you, sir. Thank you. Thank you. ಹ. ಎಲ್ಲರಿಗೂ ನನ್ನ ನಮಸ್ಕಾರಗಳು. Very warm greeting to all of you. I deem it a great pleasure to present a talk on the topic educational facts about the sun and solar supergranulation. We are looking at the enchanting image of the solar system, with the sun being at the center, flanked by 8 various planets orbiting in various orbits around the sun. Our blue-white jewel, that's home planet Earth, is suspended in the vastness of space. See, the huge mass of hot glowing gas of the sun has strong gravitational pull that holds all these planets in their respective orbits without them flying away. And in fact, the region between the orbits of Venus and Jupiter is the habitable zone or the ecosphere where life can exist, but it is only the Earth which is decreed to be at some optimum distance from the sun, which has harbored life, and we have to be very, very thankful. And heat and light of the sun has influenced all of these objects in the solar system and has allowed life to exist on Earth. Without sun, there is no life. So many a times sun is God. And I mean, it is always so, because without sun, there is no life. And there are temples built across, in some places across the world. And one such temple that I know is the Temple Ra in Egypt. Next, please. It is not in slideshow, sir, please.
Yeah.
Let it be
Slide.
slideshow.
You do it. Raman is going.
Yeah. Yeah. I am honorary professor, as introduced by Professor Swami anyway, and he is told already. And I have carried out research work at the Indian Institute of Astrophysics under the guidance of Professor Jagdev Singh and Professor Vinod Krishnan, and a very active collaboration with Dr. R. Shrikant. Next slide, sir, please. See, my talk is actually aimed at mostly at the basic level, but towards the end, I have included my research work, which I will explain later on. All space, time, and matter were created when a tiny, incredibly small, energetic dot exploded about 15 billion years ago. This is nothing but the Big Bang theory put forward in 1931 by the Belgian priest Georges Lemaitre. The Big Bang explosion would have created enormous amount of heat and radiation, which is lurking even to this day as weak radio signal, and is discovered as cosmic microwave background radiation by Penzias and Wilson of America in 1965. See, after about 300 million years gap, the galaxies began to slowly form. One of the galaxies is our own Milky Way galaxy, the Akashaganga. Okay? And It is a spiral galaxy, and our solar system is housed in one of the spiral arms of this galaxy. And there are about 200 billion galaxies, and our Milky Way galaxy has at least about 400 billion stars and their families, and it's about 1 lakh light year across. Next slide. Next. Let's have a quick look at the solar statistics. Our sun is an average star with a medium size, age, and temperature. It is already 4.6 billion years of age. In astronomy, we speak of very large scales like billions, millions, light years, parsecs, etc. And it has shone continuously for these 4.6 billion years, and now it's going to shine next for 7 billion years too. It's a large, massive object with a radius 6.95 into 10 power 8 meter. And if it were hollow, it could fit about 100 Earths into itself. And it has a mass of 2 to 10 power 30 kg. It is mostly a gaseous ball and layer. Different layers have different rotational speeds. At the equator, it is 25 days period, and at the pole, it is 32 days. Next, please. Next slide. The average distance of the sun from Earth is 1 astronomical unit, which is 150 million kilometer. And Proxima is the red dwarf star. It is the nearest neighbor to our sun. It is 4.3 light years from our solar system. Next, next. It was actually the Greek philosopher Aristotle who actually first observed the solar system. But his theory was geocentric theory with Earth being at the center. But of course, he conceptualized the various sky objects to be in various concentric spheres, etc., etc. But his theory did not gain ground. Later on, it was Galileo who invented his refracting telescope and directed it towards the sky and identified sunspots on the sun, and also he he observed the phases of Venus. So next, please. Next slide.
Next slide.
Next, sir. So let me show you the cutaway view of the sun to explain.
No, previous. Go back to previous. Wait for some time.
Yeah. So this is the cutaway view of the sun, so that I could explain much better with this image. So we are looking at, the anatomy of the sun can be explained better with this arrangement. The central portion of this sun is the core, which is 15 million Kelvin in temperature, and at this very high temperature, 4 hydrogen atoms combine to form a helium nucleus, together with the release of enormous amount of energy in the form of gamma radiation, gamma photons. These gamma photons travel towards the surface of the sun and en route, they keep colliding with other molecules and keep losing energy. By the time it reaches the surface of the sun, it mostly is converted into visible radiation, and it comes out as visible radiation that we see actually in the sky. And then overlying this core is the radiative zone, which occupies a region between 25% and 70% of the solar radius. Here also the temperature is quite high, 4 million Kelvin, and heat flux transport is mainly by photon diffusion in this region. Overlying this radiative zone is a thin tachocline layer, which is not indicated, but it is there. It is 100 kilometers in thickness, and it is the seat of magnetic field of the sun, where magnetic field of the sun is generated through dynamo action. And above this is the convection zone, which is my area of work. Yeah. And here, the convection zone occupies 30% of the solar radius below the photosphere, and convection is revealed on 4 hierarchical scales: the granulation, mesogranulation, supergranulation, and giant granulation. But much studied are the granulations and supergranulations, and my specific area of research is in the field of supergranulation. Actually, if you observe the solar photosphere through high resolution instruments, we find that it's not a tranquil, featureless surface, but is beset with granular appearance. These are a visible manifestation of the subphotospheric convection currents, which contribute to the outward transport of energy from the deeper layers, thus maintaining the energy balance of the sun as a whole. Convection is actually the chief mode of transport in all cool stars, such as the sun. And convection zone of thickness, I told you already, of 30% star radius lies in the subphotospheric layers of the sun. Here the opacity is so large that heat flux transport is not by photon diffusion but is by convection. And convection is revealed prominently. There are four, hierarchical scales, but the much studied and more prominent are granulations and supergranulations. Each granule is about 1,000 kilometer across in diameter, and its lifetime is about 5 to 10 minutes. The supergranule diameter is about 30,000 kilometer and lives for 24 hours, may sometimes even live for 2 days as well. Above the convection zone is the photosphere that we see in the sky as a bright disk. Its thickness is, as we know, it's 500 kilometer thickness and temperature 6,000 Kelvin. Overlying is the reversing layer, which is 800 kilometer thickness and temperature 4,500. For example, any element in the reversing layer is not indicated here, but it's just a thin layer here, 800 kilometer thickness about this. And any element that absorbs radiation coming from the hot source sphere, and it itself, it absorbs that radiation which comes from the hot source, which it itself emits when heated to incandescence. That is nothing but going to create what is known as absorption line. So such absorption lines were discovered by Joseph von Fraunhofer much earlier, and then at least about 62 elements were discovered in this manner in the sun. But mostly the sun consists of hydrogen and helium. 90% of the gas is nothing but hydrogen, and about 8% helium, and other elements are there also in very small percentage. And then overlying the reversing layer is the chromosphere, which is about 15,000 kilometer in thickness, and its reddish hue is because of the presence of H alpha. And also there are some features like this. There's a prominences, which are nothing but the loops of plasma lurking. It is anchoring the surface of the chromosphere. And above the chromosphere is a thin transition zone. Once again, it is not here, but then there is a layer here. It is 100 kilometer in thickness. The temperature enormously increases in this thin zone from 30,000 Kelvin to 1 million Kelvin. It is enigmatic as to how this temperature gradient could exist in this thin layer of transition layer. And overlying the transition zone is a corona layer, and which of course appears as a very bright region during solar eclipses. And there are also these spicules which actually border the supergranular convective eddies, which I'll explain later. And we are also looking at some black spots here, which appear only during solar maximum, known as the sunspots. Sunspots are nothing but the magnetic blobs, and they are looking small, but then some spots are as big as even the size of Earth. And this, because of magnetic field, they inhibit convection, and hence the temperature gets as low as 4,500 Kelvin. In terms of the rest of the sun, and therefore it appears dark in comparison with the rest of the surface. Next slide, sir, please. Next. So patches of the sun oscillate up and down with a 5-minute period of oscillation, and in the convection zone as well, there are, due to the turbulent nature of the convection, acoustic waves get generated, and they reflect off from the surface of the sun and set the sun into vibrations known as the P mode vibrations. And there are also other modes of vibration of the sun, which I am not going to discuss here, but the most important ones are this 5-minute period of oscillation and the P mode vibrations. Next, I just pointed out about, no, previous slide, please. Previous one. Yeah, sunspot cycle is nearly 11 years, change the sun's activity.
Hello, sorry for interruption. There is lot of echo.
Echo?
Yeah, we hear both the voices, your voice and also echo. Unable to follow.
Probably
Okay.
you
But
switched on that YouTube
some,
live near to the mobile is there. Might be
yeah,
you are
yeah,
getting.
USB. Yeah, please, I think audio has to be switched off.
Keep
Are you-
away the YouTube from your this thing actual.
Yes, yes.
Zoom. Okay, please now try.
Yeah. Now is it okay? Yeah. So sunspot cycle is a 11-year cycle where the activity of the sun keeps increasing, slowly increases, becomes maximum, and then it diminishes gradually. It is because of the presence of the sunspots. Also, there is a 22-year magnetic cycle where there is a reversal of magnetic poles at the solar magnetic polar region. Actually, we are in the 25th solar cycle, which started on in December 2019, and the maximum occurs between 23 and 26, and we are actually in the phase of solar maximum right now. Solar cycle
Again, there is
24
echo.
was the
Sorry.
previous cycle, which was
Hello. Very sorry, there is echo again.
yeah.
Maybe another co-host is also opening. Please stop audios of all the people.
Yeah. Yes. Yes, sir. Now it's okay. Yeah. So the period between 1645 and 1715, with very few sunspots, is known as the Little Ice Age, where the North Atlantic region became very cold, and the activity of the sun diminished so much, and the volcanic eruptions raged much more, and plantation died, and there was famine. It was
No,
the
madam.
under
It is,
minimum.
I'm sorry to say that we hear lot of
Ah,
echo.
Malesh,
Are you using?
there is no problem.
Are you
Malesh,
using two systems?
Dr. Malesh,
No,
Ah,
your voice is reverberating
yeah,
uh,
my speaker's voice is also doing same for me.
because we are able
yes.
to hear her quite nice.
Sir, once log out and log in, sir, your voice will be clear.
For us, there is no audio problem.
No problem. Yeah.
Clear. It is very clear.
Okay. I'm okay.
So, Malesh, you have to mute your this thing,
Those who are not speaking, please mute your microphones till the end, please. Okay, please continue.
Yes, sir. So, so the 11-year pattern is known as sunspot cycle, and I will explain to you about this interesting excursion of the sunspots across the solar equator in the next slide, please. Let's go to the next slide. Next slide, please.
Come on, next slide.
So the sunspots originate at plus or minus 30-degree latitude usually, and they drift towards the equator as the cycle progresses. And the next batch of sunspots originate at slightly lower than 30-degree latitude, and once again that same phenomenon repeats itself. And by the time the cycle gets completed, the profile of the motion of this spot would be something like a wing of a butterfly. So this is one cycle, but considering all the cycles, many cycles, it gives us a pattern of butterfly, and that is known as the Mondel's butterfly pattern of the sunspots. It is still not understood as to why this kind of behavior of sunspots is happening on the sun. Okay. Next one, please. Next slide. Yeah, what happens if the sunspots are no next
Back.
previous one, please. Previous
Yeah.
back.
Wait.
What happens if next? Yes. Okay, correct. What happens if the sunspots increase in number? It is going to result in what is known as the solar storms. Solar storms occur very close to their sunspots along the neutral line between the opposite magnetic fields. And it is nothing but a combination of solar flares and coronal mass ejections. Solar flares are nothing but huge bursts of energy and mass and energy from the sun. It consists of energetic electrons, protons, and energetic photons of ultraviolet radiation, X-rays, gamma rays, etc. These are just expelled from the sun into the space, and it can reach. It would, if it is a large flare, it would reach the Earth's magnetic field, and it gets deflected from the magnetic field. Some of these spots can manage to reach the polar region of our Earth. There they interact with other molecules of the polar region of the Earth, and excitation and de-excitation mechanisms can result in the display very colorful, beautiful curtains of light in the northern and southern hemispheres. It is known as aurora borealis in the northern hemisphere, and aurora australis in the southern hemisphere, known as the southern light. But some flares last for a few minutes, but some flares last as long as an hour or two. And traveling at the speed of light, it takes 8 minutes for the light from the solar flare to reach the sun. To reach our Earth. They are nothing but sudden, tremendous, explosive outbursts of light and material from the sun. Next slide. See, one effect I told you already, but the other effects can be very ill effects. Can be the geomagnetic storm. It's a major disturbance in Earth's magnetosphere, and because of the kind of geomagnetic storm, there can be a temporary delay of frequency identification and satellite navigation. And some electronics equipments in the satellite can get disrupted. Even if there are astronauts in space, they will also get affected if there's a large flare. It's a very grave effect of the solar flares. But the most significant threat posed by geomagnetic storms are on the power grid. These energetic particles with high pressure strike the magnetosphere of our Earth. It deflects or it fluctuates the magnetic field, which results in the induced current due to electromagnetic induction. That appears as ground current in the transformers on the ground, and they can if the ground current is high, it is known as geomagnetically induced current. If the ground current is high, it can melt the copper windings, and it can result in massive power shutdowns and blackouts. So that is a very grave situation. One such very strong geomagnetic storm occurred in 1859. It was known as Carrington event, when in a very large flare accompanied by coronal mass ejection. A large flare is usually accompanied by coronal mass ejection. It struck our Earth, and it actually resulted in fire also in a telegraph station. It is. And there were very large aurora displays in the northern and the southern hemispheres during this Carrington event. Okay, next slide, please. Next slide. Yeah, this is one flare event that you can see, and this is coronal mass ejection, which I borrowed from the net. Yeah. Next, sir. So this is a beautiful display of color in the sky. It's in the higher latitude regions.
Previous.
That is aurora. So now, yeah, that's okay. Yeah, this is a very colorful display. Now, space weather is a branch of space physics and aeronomy. Aeronomy is the study of upper atmosphere, concerned with the time-varying conditions of the solar system. Space weather occurs when the solar star travels through space and impacts the Earth's magnetosphere. Space weather knowledge is very, very important because it can affect our national economy due to the fact that we are dependent so much on the advanced technology nowadays, and it can, disrupt the satellite navigation and things like that. And therefore, we have to study about the space weather very carefully and on a day-to-day basis. And see, I have told already about this astronauts. They are sent to space into the collection of large flares and coronal mass ejections. Yes, next slide. So this is the thing. The magnetosphere, which is about, the magnetic field surrounding our Earth. It is about 10 Earth radii on the sun side and 60 Earth radii on the opposite side of the sun. Yes, next. Now, what happens to the sun after many, many billions of years? Say about 3.5 billion years, sun will be twice as big as now. It will be a hostile planet with Venus, and in 5 billion years from now, sun will be 200 times as bright. 200 times big, and 2,000 times as bright. It will be like a red giant star, engulfing planets like Mercury, Venus, Earth, and Mars. All those surfaces cooler, it is going to shine 1,000 times more brightly. The core will be a carbon core. Of course, helium core that got converted into carbon in thermonuclear reaction, and that is so hot that it emits ultraviolet radiation at that very high temperature. This radiation has so much energy that it will drive enough for hydrogen gases into the outer space as planetary nebula. Yes, next slide, please. Next. What decides the end state of the star? No,
Previous. Wait.
What decides the end state of the star? That can get converted to. Please go to the previous slide. Previous. The one the neutron star of the planet. A white dwarf star is going to happen when it is going to appear when Schumacher mass is less than 4 solar mass. And it settles down as white dwarf finally.
Why we are not hearing you? Please.
Sir, problem data signal, sir.
Oh, is it?
Yeah, madam is facing a data signal issue.
Oh. Wait.
Sir, video switch off ಮಾಡಿದ್ರೆ ಕಂಟಿನ್ಯೂ ಬರುತ್ತೆ ಸರ್ ಆಡಿಯೋದಲ್ಲಿ.
I'll inform, sir. I'll inform.
Video off ಮಾಡಿಬಿಟ್ಟು audio ಇಟ್ಕೊಳ್ಳಿ. ಹೌದು, correct.
Okay, I'll inform.
Phone number ಇಲ್ಲ.
I'll speak with her.
Off ಆಗ್ಬಿಟ್ಟು
Sir, ಅವರು ರಿಸೀವ್ ಮಾಡ್ತಾ ಇಲ್ಲ ಸರ್.
ಅಯ್ಯೋ.
And
now it's okay.
what happens? I don't know what happens.
We are not getting your voice. Please switch off the video and only you use the voice on microphone. That will be better. I think there will be disturbance. Your video is giving
Okay.
without the video. Please continue without video. Okay.
Okay. Now it's okay. Yeah. Yeah. The white dwarf has a carbon core with degenerate electrons around it. It has a mass to the sun packed into the radius as small as that of the Earth. That means we can imagine the kind of density. One teaspoonful of this white dwarf is supposed to weigh as much as an elephant, they said. I mean, it is so dense. But if the initial mass of the star is greater than 4 solar masses but less than 10 solar masses, then it cannot withstand the gravitation contraction and collapse continuously. And the temperature increases to 600 million Kelvin at the core, and carbon gets converted into magnesium and then to oxygen, silicon, and finally iron. Iron marks the end stage of thermonuclear reactions. If during this collapse, if the final mass of the collapsing star approaches something like 1.44 solar masses, it is going to explode, and it is known as the supernova explosion.
Yeah, now we are getting no problem.
No problem, yesterday. No problem.
No problem. We continue without video. That will be all right.
Yeah. Yes. So, Chandrasekhar mass is 1.44 solar masses during the collapse of the star. So, it was Professor Chandrasekhar who received the Nobel Prize in 1983 for his work on evolution of stars and white dwarfs. He shared this with William Fowler as well.
ಮತ್ತೆ ಆಡಿಯೋ ಪ್ರಾಬ್ಲಮ್ ಆಗಿದೆ ಸರ್.
Next slide. Next slide. Yes. So this is supposing the progenitor mass is more than 10 solar masses and less than 25 solar masses. It is going to explode into supernova explosion, and it can either turn into neutron star if the degenerate electrons capture the protons and convert themselves into neutrons. In the star, you find only neutrons, and these are known as neutron stars. Some neutron stars are rotating and known as the pulsars. But if it is so high, the progenitor mass is as high as 25 solar masses, then it is going to be doomed into what is known as a black hole. And black hole is so dense that not even light can be seen coming out of this star, and nothing can enter into and nothing can come out. It can be only detected by the accretion of material from the nearby stars, and that is the black hole. And you are looking at the black hole animation here in this slide. And it so happens that the gravity is so high that it bends the space around. So that is, space is bent because of the intense gravitational field around a black hole. Yes, sir. Next slide, please. So now you are looking at an image where I have been showing you some points known as the Lagrangian points. These mark positions in the Sun-Earth orbital configuration where the combined gravitational influence of the Sun and Earth provides precisely the centripetal force for any lighter object that is placed in one of these Lagrangian points to orbit with them. The advantage of placing the satellite in these points is it can observe the sun without any occultations and eclipses. In fact, there are 5 such points in the Sun-Earth orbital configuration. That is L1, L2, which are 1 kilometer from the Earth, L3, which is 300 million kilometer from Earth, L4 and L5 are 150 million kilometer from approximately. L4, L5 is approximate. 150 million kilometer from Earth. So in fact, our Aditya Space Telescope is placed at L1, Aditya L1, and James Webb Telescope is placed at L2. Okay, next slide, please. Aditya L1 is a spacecraft being designed in India, and its mission is to study the sun. It was actually conceptualized by the Advisory Committee for Space Research in January 2008, and with the collaborative efforts of many of these organizations like IAA, IUCA, ISRO fundamentally, and all these organizations came together to launch this spacecraft Aditya L1 to study the sun. It has been placed at the Lagrangian point L1, which is 1.5 million kilometers from Earth. So far, only NASA and ESA have been successful in placing the satellites at this point L1. But we have now done this, and our IAA has one payload in this, that is SOOT, Solar Ultraviolet Imaging Telescope, which has some 11 filters, and it studies the various layers of this corona. The basic purpose of this Aditya spacecraft is to study the high temperature of the corona. What could be the reason for extremely high temperature, like 1 million Kelvin of that of corona? So that is about Aditya spacecraft. Next, we go to the next slide, please. Now let us think of this extraterrestrial life. What if there is any alien signal elsewhere apart from our own planet? See, our beautiful Earth shines like rare blue and white jewel, I think, and there are forests, mountains, flora, fauna, which we are just enjoying day in and day out. And no one knows if extraterrestrial life off Earth exists. So, Search for Extraterrestrial Intelligence is a project which was begun by Americans in 1976. The argument is, if life can evolve through a chemical and physical reaction from the non-living molecules in a series of physical and chemical reactions, it is not a unique cosmic accident as well, then life could probably exist elsewhere. See, this kind of transition from non-molecules to living molecules has happened on Earth through evolutionary processes, the chemical processes and things like that. So we can also expect such a thing to have happened elsewhere in the other parts of the universe. That is the thinking. This next. So these are the various missions to study the extraterrestrial intelligence. In our own solar system also, there is some inkling about the sustenance of life in some, even in satellites of large planets like Jupiter, etc. But that has not been found still. So it is the search is still going on. Next, sir, please. There is one planet like Proxima b, which is orbiting this Proxima Centauri, our closest red dwarf star, 4.3 light year away, which could harbor life because the temperature of this planet is almost conducive for the presence of water and atmosphere. I mean, presence of water, atmosphere, we don't know. So it is one speculation about this Proxima b. So next slide, please. Astronomers are planning to look for 7 planets that orbit the star called TRAPPIST-1, which is 40 light years away. So 3 of the planets are supposed to occupy the Goldilocks zone, that is the habitable zone. The most important condition is not just being in the habitable zone, but also there should be atmosphere. If X-rays and UV radiations, very high energy radiations, expel this atmosphere, it is not possible for life to sustain. So it is important for both the planet being in the habitable zone and also to have the atmosphere and water for the sustenance of the race. That's important. And now there is one more effort by NASA's Kepler Space Telescope to discover Earth-like planets elsewhere, apart from our own solar system. That is 186F is nearby red dwarf star, which has this Kepler 186. 186F is the name of this planet, which is orbiting the star Kepler 186. It is in the Goldilocks zone, and it is 580 light years away, and perhaps there could be life, and that is being still efforts are being made to find out. And the most powerful space telescope to search for extraterrestrial life is James Webb Telescope, launched on 25th December 2021. It is spying on planets and it is looking for alien signal elsewhere uh, apart from our own solar system. Next. So there is one huge spherical 500-meter radio telescope commissioned by China in Guizhou province and at the cost of $80 million. And it has tried to get some signals from pulsars. Of course, it's not being able to. The basic idea is to search for biosignatures, but elsewhere apart from our solar system, but it's not been still successful. But efforts are going on again. It is the British astrophysicist Stephen Hawking who has warned us against, any search for extraterrestrial intelligence, because according to him, one day we might receive a signal from a planet like Gillies 832c, which is about 16 light years away, and it is so powerful that the civilization in that planet could be so powerful, they may treat us like minuscules, like bacteria. Of course, that is just a caution given by Stephen Hawking. So next one, please. See, actually, before I go to my area of work, I would like to tell you these astronomers are also collaboratively working with computer professionals to leverage algorithms of this artificial intelligence and machine learning to, to analyze space data, recognize patterns, and make predictions. So this technology is very important to find out the existence of exoplanets and extraterrestrial intelligence. In fact, even nanoscale robots and rovers are launched to for this kind of autonomous exploration to find out about the kind of environment elsewhere in the universe apart from our solar system. Okay. Now coming to my work, I have handled this intensitygram and Dopplergram. Intensitygram is the photograph of the sun taken in a specific narrow region of wavelength, typically centered on a Fraunhofer line such as H alpha and calcium 2K. And Dopplergram is a surface velocity map of the sun. I have handled these two data. In fact, you can see this dark bright patterns. It's more prominent here in the Dopplergram. These are nothing but the large convective eddies, which I mentioned as supergranules. I have, in fact, handpicked and visually picked these, supergranules through a computer program. I just, select individually these supergranules. It's a very laborious process, but it's a foolproof way of doing it. And I have characterized these supergranular cells by determining its length scale, means diameter, horizontal flow velocity, area, perimeter, and lifetime, and fractal dimension. In order to establish interrelationships amongst these parameters to find out if it is in consonance with the Kolmogorov's theory of turbulence, which is an important theory in the theory of turbulence. And in fact, I have used the fractal dimension, which is a very important mathematical tool to gain insight into the underlying dynamics. It is very important for quantifying these supergranular cells, and it helps in analyzing very well. So next slide, please. I have already explained to you about this, so we'll go to the next one. Next one. Yeah, this also supergranular animation. You can see this matte pattern. Yeah, this is also solar convection, and initially I have given you a brief description of solar granulation and supergranulation. Let's move on to the next one, please. Yeah, sometimes supergranules are believed to be caused by prograde waves. In some research articles, this is the thinking, with the 6 to 9 days period, it's said. But Most often, the supergranular flows are studied with particular attention as they are closely related to the magnetic field distribution of the sun. So it's very important that one has knowledge of the supergranular features so that the distribution of the magnetic field in different parts of the sun could be understood. Yeah, next one, please. Actually, supergranules manifest regions of horizontal flow diverging from the cell center and declining flows at the cell borders. So these flows, the plasma flows, I mean, the plasma flows transport magnetic field, shreds of magnetic field from the declining active regions to the borders of the cell where they accumulate. At the borders of each cell, the magnetic field gets accumulated, generates intense heat and creates what is known as a chromospheric network. Chromospheric network is a level tracer of supergranulation. So whatever features apply to supergranules apply to chromospheric networks as well. They are no different. Yeah, next please. And I have picked this particular graph. I mean, then in the next slide you'll see that that's a plot of supergranular horizontal velocity amplitude versus flux density for a region at a heliocentric angle of 40 degrees. It shows monotonic decrease. That is, as the magnetic field increases, the horizontal flow velocity decreases. That means it establishes this fact that there is accumulation of the magnetic field at the cell walls. Yeah, next slide. Next slide. So this is one slide that I have I'm showing you, where the magnetic field accumulates towards the borders. As you can see, this is this picture I have. I mean, this plot I have borrowed from the thesis by Raphael Atty. So next one, please. Next one. I have analyzed 33-hour data from SOHO. That is, I have picked 33 data of Doppler grams, and I have also analyzed intensity grams from our own Kodaikanal solar observatory. Doppler grams are during the solar minimum phase, and my intensity grams are during the solar maximum phase. Yes, next, please. And analysis has been done very carefully using only computational methods. See, selecting the data itself is challenging. The data of both intensity gram and Doppler gram have been obtained with a resolution of 2 arcsecond, which is twice the granular scale. So this itself submerges the granular signals. And I have integrated over 10 minutes interval, means I have averaged over 10 minutes, so that 5 minute, 5 into 2, 5 minute period of oscillation is annulled. Also, the granular signal also gets weakened, completely weakened, and it's almost like it's not there at all. And now I also have taken care to apply corrections due to solar rotation, due to Doppler shifts which come up, and that has been again done computationally. And the cells are chosen only between 15 degree and 60 degree angular distance limits because it reduces effects due to projection effects and foreshortening effects. The error due to these two get minimized. So with all this care, data has been analyzed, but our sample is quite small. Only 200 cells have selected for from the SOHO, and it's about 57 because you know it's a visual inspection which is very laborious. But it is a foolproof way, I told you, and the result is guaranteed. Supergranular field very closely agrees with Kolmogorov's spectrum. VH equals epsilon per 1 by 3 L bar. VH is something but horizontal flow velocity. Epsilon is the energy injection rate, and L is the length scale of the supergranular. Length scale is nothing but diameter, and also VH, V subscript H equals epsilon per half and T per half. These two papers were published in MNRAs. Okay, next. Next slide. And the size of the supergranular cell is obtained by parallel scans across the cell restricted by the observed cell boundary. The true size is obtained from the measured size by correcting for projection effects. the area perimeter relation is used to evaluate the fractal structure because P equals A power D by 2, where D is the fractal dimension. And lifetime is analyzed in this manner that we select usually a larger window, 33-hour data, because we know that approximately is about 24 hours. And we identify the birth of the cell at one particular window and keep tracking that same cell during the progressive consecutive windows. And in one particular window, it vanishes completely. So the lifetime is identified as a time interval between the first appearance and the final disappearance. And coming to the velocity, line of sight velocity can be easily read off from this velocity scan. We just usually read it out. And by using a specific formula, we find out the horizontal flow velocity of these cells. Next, please. So the main results pertaining to the maximum, minimum, mean and standard deviation for the cell of area A and perimeter P for both the Doppler-gram and intensity-gram data are summarized. And the area distribution of Doppler-gram shows an asymmetry with a steeper rise on the smaller scale and gentler fall on the larger scale. It peaks at a characteristic size of about 8 into 10 per 8 kilometers square or a diameter, because I will show you in the next slide. Please go to the next slide. Here the maximum, this is like a histogram and this is also like a probability curve. This is the maximum, the most probable area of the supergranular cell, which is actually about 8 into 10 per 8 kilometer square. And pi r square is that. Now it's a simple fundamental school mathematics. Pi r square is and that is 8 by 5 square root of that into 10 power 4. That gives r. Twice of that gives the diameter. By this method, I got a value of 31.9 megameter, which is very closely agreeing with the theoretical value of 32 megameter for a supergranular cell. Of course, there is a range of sizes, of course, but this is the most probable size of the supergranular cell. Next slide, please. So, and my student, Dr. Soumya, PhD student, has studied about the lifetimes of these supergranular cells across various latitudes. She has found out that the lifetimes of these cells are almost the same, as you see in the next slide. Go to the next slide. Next one. They are almost same in the quiet region, but the lifetime is less. It is between 20 and 30 hours for the quiet region, and for the semi-active region, it is between 30 and 40, and for the active region is maximum between 50 and 60. But nevertheless, the lifetime is almost constant across various latitudes. This work has been done by her, by Dr. Soumya. Okay. And my other student, Dr. Rajini, also has studied about the fractal dimension across various solar cycles, and she has also obtained very good results. Both of them have published papers in peer-reviewed journals. Okay, next please. So this is a tabulation of various parameters of the supergranular cells, and I have also computed skewness and kurtosis as statistical parameters. Skewness is departure from the symmetric distribution of this the various parameters, and kurtosis is peakedness of the curve. So these are some of these. You just have an idea as to how this is tabulated and the kind of values that are obtained. Yes, next one. Next one. Yeah. I have obtained. Sorry. The linear relation suggests that supergranules are self-similar and may be regarded as fractal objects. I have used this relation P proportional to A per D by 2, where D is the fractal dimension, P is the perimeter, A is the area. So D is an important parameter. I told you, is a fractal dimension is an important tool to quantify the supergranular structures in order to gain insight into the underlying dynamics. So that's a very important thing that has given us very good result. And in fact, I have made use of Kolmogorov's theory of turbulence. According to this theory, if the supergranular feature is like an isotherm, it follows this it has to have a value of fractal dimension being 1.66. On the other hand, next one, please. Next one. If it is an isobaric in nature, by this formulation, you could get a fractal dimension of 1.32. But my data has obtained a value of 1.23, which is almost close to 1.33, you can say. And so consider the supergranular network to be isobaric in nature. In fact, it's very interesting that even Rudier and Muller have obtained similar dimension for smaller granules, that is granulation. But unlike in granules, ours shows a single linear fit, suitable for the entire observed range of supergranules. So the self-similarity exhibited by a large range of scales of convection lengths support the turbulent convection based on a horizontal flow velocity, lifetime and length scale data for supergranulation. But of course, it is very important that we have to study the relative merits and results using other data sets, not only Dopplerograms and intensitograms, but magnetograms, not only different data sets, but also different resolution data sets. I have used 2 arcsecond, but one can use even 0.6 arcsecond data set to better understand the convection phenomenon. So it is instructive to explore the relative merits of various data sets and different resolution data sets. So this is my work. And next slide, please. This is the typical plot of log P versus log A, which gives me the fractal dimension. This I have already explained to you about this. So its a correlation coefficient is much high. It is about 0.95 or something like this. So next one. So my talk ends here. I thank the President of Karnataka Physics Association, Professor Raj Kagli, for inviting me to give a presentation. I thank Professor Rudraswamy for introducing me to Karnataka Physics Association and for initiating to arrange my talk. I thank the Secretary, Professor Nagaraju, and Dr. Raghavendra and K, and all the committee members of Karnataka Physics Association. And I thank all the listeners of my presentation. I thank the collaborators of my research work. I particularly thank my guide, Professor Jagdev Singh, Professor Vinod Pishim, and my very good collaborator, Dr. Rajiv Kant. And thanks to one and all. Thanks a lot.
Thank you, madam, for a very nice presentation. Now it's
Thank
time
you,
for
sir.
some questions and comments. Anybody would like to ask questions, they may raise their hands and then ask one by one, please. Any question? We can start with anyone who wants to ask a question. Few questions, brief question, briefly. Rudraswamy, please ask your question.
Yes, sir.
Rudraswamy, you have raised your hand.
Very informative talk, madam. Thank you very much for exciting
Welcome,
talk.
sir.
Your question, go to the question, please.
Madam, what is the status of performance of Aditya space satellite launched
Telescope.
by ISRO to go around the sun? There is no updates and news on its performance.
Yeah. No, there is actually, it is only collecting data, but not much outcome has been there from this telescope. But it takes some time, I think. It takes some more time to, find out.
Okay.
Thank you, madam. Thank you very much.
Professor BK, if you can allow me to make one statement, because
okay,
it's
please do.
in Aditya where I am involved.
Please do.
Just an update, sir, Rudraswamy sir and other
Thank you.
members. The Aditya satellite is in very good condition. Data is being harvested, except one of the small things in Welk. Otherwise, all other X-ray payloads are excellent. Data is being given. Many 2-3 research papers also I have personally seen, but many people are drafting, because at this time we call it as a performance verification phase, PV phase we say, where
Yes.
right of operating the instruments on board satellite is vested with the only payload operation center. I mean, the instrument who has designed, developed. However, there are some collaborators who are working with all these payload operation centers. They are having a secondary access of the data. However, we have released the data in our ISRO website. People can access the data. All data last, I think, January 16th, if I'm not correct, January, you can take. January 16th, we have released data. More than 8 terabyte of data is made available to the public. Global community are accessing data. It is only 6 months now. Generally, one data set comes to a researcher, it takes years to analyze and do it. But hopefully, we will see good number of whatever the instrument scientists they have done. Some papers are in public domain. Data is also in public domain. Overall, satellite is in good condition, except in limited something is there. Otherwise, it's quite good. Whatever in the first attempt to go to the Lagrangian point and give such kind of a huge amount of per day, we are getting more than 200 GB, 300 GB data, which I am part of that one. That's the reason. Sorry for the
Very
speaker
good.
if I
Very
have
good.
taken extra time.
Thanks to Dr.
No,
Srinath
no,
for the
no,
information.
no
Thank you
problem at all, sir. Thanks for the update. Actually, it reached L1 on 6 January 2024. So it has been almost more than 1 year since it is been
Okay,
there.
we'll move on to Professor Balkrishnan. You want to ask a question, please? Professor Balkrishnan, please ask a question. You have to unmute your microphone and then ask. Balkrishnan. We are not hearing you. Unmute your microphone is muted.
Sir, Professor Balkrishna, please unmute your phone.
Muted. We are not hearing you. Your microphone is muted.
Unmute. Unmute.
Okay, we will go on to another question. Perhaps somebody else would like to ask. Oh, I have a.
Do you hear me
Yes,
now?
he is now
Now
online.
unmuted, sir, by Sir Balakrishnan. Unmuted.
Okay, please ask.
Thank you for giving me the chance. It was a well-organized, informative, crisp talk by the speaker, and
Thank you, sir.
congratulations, sir, for this. My question is about the effect of sun's magnetic field on the disturbance that we get in the communication systems now. They say that
Yeah.
the solar flares causes magnetic field variations, and one group
Yes.
has said that that's the reason for all over the disturbance in the communication. Is
Yeah,
that
the communication net. Yes, yes, please
Okay, please answer.
tell me.
Please answer, Dr.
Yeah, see, if it is a very large flare, it is going to emit copious plasma particles, very energetic particles, and also the energetic photons, which can disrupt the communication network, which can strike the electronics in the satellite communication system. It can disrupt. So that is the reason. The magnetic field in the solar flare gets converted into kinetic energy. Magnetic energy gets converted to kinetic energy, and these high energy particles are hurled into space, and they can strike the electronics of this communication satellite systems, and it would pose dangers for the communication problems.
Thank you.
I mean,
I have
so
a
that is the reason.
I have a basic question, if you don't mind. That
Yes,
is,
sir.
what are the factors that determine the sizes of granules or super granules? So what are the physical factors that contribute to the sizes of these granules? Could you elaborate on that?
You mean to say, what if the size of the supergranule is larger? And things like that?
What are the factors, physical factors that determine these the granules as well as super granules, and how
So it is, the plasma outflow pressure from the center to the edge of the cell, that determines actually the size. In a smaller supergranular cell, the outflow pressure is very large, and therefore it is almost like a circle. Whereas in larger supergranule, it is less, because it has to travel more distance. By the time it travels larger distance, it loses that energy. So it reaches the borders of the cell with lesser energy, and it creates corrugated boundary, and that is more fractal in nature. Fractal is nothing but corrugated. Yeah.
Even
Denticulated.
thank you. But even more basic question is, why do we actually have these granules and super granules? More basic question. Why we have these granules and super?
It is granules are originating from different depths under the surface of the sun. Super granules originate at another depth. So no one knows as to what is the main cause for the origin of the super granules, from which depth and things like that. So helium ionization is responsible for the generation of the super granules. It is speculative, but nothing has been ascertained. So
Thank you.
So, yeah.
Any other questions? Dr. Srikanta, you have a question?
Sir, Mallesh, I am
Professor Mallesh, yeah, you ask a question.
First of all, I am extremely sorry for the fault was at my end. Dear speaker, kindly excuse me.
Okay.
Second
No
comment
problem,
is,
sir. No problem.
I am so happy that one of the main areas in mechanics and our sun is providing such a nice arena or domain for studying chaotic dynamics. Thank you. You mentioned about those things. I am happy to hear that.
Any questions?
Thank you, sir.
No questions. Okay. Any other person? Okay,
So
Professor.
I will request Professor Paniveni Madam to render a.
No,
Yes,
before
sir.
that, there is one question. Srikanta is there. Professor Srikanta wants to ask
Yes,
question.
sir.
Okay, please ask.
Madam, can we refer to that slide on black holes, white dwarfs, and this thing? Like,
Yes, sir.
We have to go back.
Yes, sir. Please go back.
Slides, I
Yes,
don't know who has to control the stuff.
Yeah.
Someone has to go back to the slides because she doesn't have control over the slides.
Yeah, I don't. Yeah, I can't do that now here from my end. Please. Yes, sir.
Professor B.A.K., meanwhile, one point I wanted to bring it to notice. Please permit me.
Please do. Yeah, please do.
No, this was
Yes,
a
next
supplement.
slide. Yeah. No, before that.
Before this?
Earlier one.
Yes, sir.
Yeah. This one, I remember to have read that you said, in the previous slide, you said that if the initial mass of the star is more than 4 solar masses, but less than 10 solar masses, they end up a supernova explosion.
It turns.
And also that finally it can become a black hole also, right?
Yeah. That's what I said earlier. It can also become black hole if the progenitor mass is more than
next slide.
25 solar masses.
What is the next
Next
slide?
slide, yeah.
So
If it is between 10 and 25, between 10 and 25 initial mass, it becomes black hole.
But it depends on the final collapsing star, mass of the collapsing star also, no?
Yeah, if it is very high mass, like 10 solar masses or 25 solar masses, when it is undergoing collapse, during the collapse stage, if it reaches the Chandrasekhar mass limit, 1.44 solar masses, then it is going to explode.
Then it can explode and go to neutron star, right?
A neutron star sometimes see what happens is, in neutron stars, these degenerate electrons, which are high pressure electrons, very high energy electrons, which occupy high energy Fermi levels, they can counter the gravitational contraction.
The remnant of the supernova explosion is a neutron star, right? The remnant of the supernova explosion is a neutron star. Am I right?
Neutron star, and also it can be a black hole. If it is initial mass is very high, it cannot be a black hole.
As the stars evolve, they'll be losing a lot of mass.
It depends upon these degenerate electrons I told. They can offer pressure to counter the gravitational collapse.
Okay.
They are very high energy electrons which occupy high energy Fermi levels, and they offer this pressure, the force against the gravitational force. And it can stabilize as a neutron star because it so happens that the energetic electrons capture the protons and get converted to neutrons. And if the mass lies between 0.7 m theta and 2 m theta, it will stabilize as a neutron star. That is a condition.
If I might just comment, what happens as the stars evolve, and they will be losing a lot of mass. That is why, if a very massive star in the range 10 to 25, they will be overcoming both the electron pressure and neutron pressure, and therefore ultimately end up as black holes. So they have to start with a very high mass to end up as a black hole.
Yes,
In the massive stars, they die early than the light stars.
No, they will collapse.
Yeah.
Srina would want to ask, make a comment, please. Srina, please.
This is regarding the communication question was asked. The supplementary answer only, not to deviate from the discussion. If you say the station ground point as a receiving point and a satellite as a sending signal point, and sun, if you treat it as a what you call as a RF noise or whatever maybe, there are three categories of outage of communication is possible. In case of low Earth, less than 1,000 kilometer, if all these 3 points in line, because there are in a day 14 orbits will be there for satellite, very rarely it will be aligning with the sun. That time only minute or 2 minute the outage of communication is possible. In 36,000 kilometer satellite category, there will be in a year or in a 3 months, 6 months, depending on that. In our geoparking satellite positioning, if sun is just behind it, the communication outage is possible. Third one is in case of Mars orbiter mission, there are two categories are there. When you are inside the orbit, we call it as a whiteout. When you are behind the sun, we call it as a blackout because of the signal which is passing through the sun's in and around the region. There is a possible. In case of Aditya L1, even though L1 is in line with the sun, earth, and satellite point, we don't position the satellite in that point. It will be in a halo orbit, which will be looking like a potato chips, and hence we will not see any communication outage. However, due to intense activities, as speaker explained, sometimes it is possible. So far, we have not done. This is one input I wanted to put. Thank you, Professor.
Thank you.
Thank you very much, sir. Thank you.
Professor Nagaraj, you want to ask any question?
ಓಕೆ ಐ ಆಮ್ ಹಿಯರ್ ಮೇಡಮ್, ತುಂಬಾ ಧನ್ಯವಾದಗಳು. ನಿಮ್ಗೆ ಸಾಕಷ್ಟು ಕವರ್ ಮಾಡಿದೀರಾ. ಯಾಕೆಂದ್ರೆ ಅರಿಸ್ಟಾಟಲ್ ಇಂದ ಶುರು ಮಾಡಿ ದೆನ್